Hello and welcome back. In this video, we're talking about limits and continuity for functions of 3 or more variables. So all of the same things we just talked about for 2 variables are true here, except again we're extending to another dimension. So here we have a function of 3 variables, which again means its domain is in R3. It's in space. And so when we had a function of 2 variables, we could approach any point in the plane from a bunch of different curves. The idea here now is our domain is in R3, and we can approach, say, the point 2, pi over 2, 0, through any path that goes through that point. The same idea, but now we're talking about space curves rather than plane curves, right? We're just talking about curves that go through this point in R3. So the limit exists. If the limit exists and is equal to L, then all limits exist along any path, any space curves that go through this point. All of those, the limit laws we did, those all work. That composition rule, that all works. And so this isn't going to be a terribly long video. I just want to show you a couple things. So we're doing x, y, z goes to 2 pi over 2, 0. So we're approaching this point. This thing, remember the graph of this function lives in 4 dimensions. It's a 3-dimensional object living in 4 dimensions. So we can't really visualize it too well, but we can still compute limits. So the idea here is, well, if I just plug in, if I try this by direct substitution, that is, this point is in the domain. This is an interior point. Because the domain is all of R3, right? There's nothing I can put in to mess this up. So the domain is all of space. So every point's an interior point of that domain. So this is an interior point, which means the limit's going to be easy to compute. We can just do it by direct substitution. So 2 in for x, so that's 2 squared, sine of y, which is approaching pi over 2, and then over z squared, well, that's going to 0, so that's 0 squared plus 4. Sine of pi over 2 is 1, 2 squared is 4, so this is 4 over 4, or just 1. So again, what this means is that the function values approach 1 as we approach the point, approach 2 pi over 2, 0 along any path in space now. And so that's pretty cool. All right, and then as I mentioned, this function composition rule still works. So if we have a function of 3 variables that looks like this, h of x, y, z is this. Well, on the outside here, I have a square root of u, where u is x squared plus y squared plus z squared minus 1. I know square root of u is continuous when u is greater than 0, and this, or greater than or equal to 0, rather. No, actually, I think I want strictly greater than 0. When u is strictly greater than 0, no, greater than or equal to 0. Sorry. Yeah, this. And so this whole function will be continuous so long as u is greater than or equal to 0. So I need u to be greater than or equal to 0. So that implies I have x squared plus y squared plus z squared greater than or equal to minus 1 is greater than or equal to 0. So I have x squared plus y squared plus z squared has to be greater than or equal to 1. So if this is true, then the function, this h function is continuous. And so where is my function continuous? H is continuous in R3 outside. So here I have x squared plus y squared plus z squared greater than or equal to 1. This is if it were equal to 1, that would be a sphere of radius 1, but it's not equal to 1, it's greater than or equal to 1. So this is all the space outside of a ball of radius 1. That's the idea here. So everywhere outside of a ball of radius 1 around the origin, centered at origin, our function will be continuous. So that's pretty cool. All right, that's it for this video, and that's it for this section. I'll see you in section 15.3. We'll finally get into differentiation for functions of several variables. Fun stuff. I'll see you there.